All right, guys, let's go ahead and get started with these net force equation notes. So a net force equation is going to help us summarize the information found in our free body diagram as a mathematical relationship. So we need to remember that forces are pushing in one direction are written as positive, and forces that are pushing in the opposite direction are going to be negative. For the sake of this class, forces that point up or to the right are going to be positive, and forces that point down or to the left are going to be negative. Since forces can either be in the x or y direction, we're going to need to write separate net force equations for each of those axes. Let's go ahead and look at our first example here. We're going to say that we have a rightward force that is being applied to a dresser to accelerate it to the right across a bedroom floor. Something important to note right here is that we're accelerating it, and because we're accelerating it, that means that we're going to have unbalanced forces. So the next thing we want to do is go ahead and draw a picture, because we always want to have a picture so that we know what's going on. So let's say here's our ground, okay? And then we have our dresser right here, and we have a person pushing this dresser. Apparently they're taller than the dresser. I guess it's a tiny little dresser. They got a giant neck too. It looks more like a giraffe, but that's fine. Next, we want to go ahead and label our origin, showing that to the right is the positive x direction, and up is the positive y direction. And I'm just going to go ahead and write that here, just so that we know for sure. Positive y is up, and to the right is positive x. After we have our picture, we're going to go ahead and draw our free body diagram. So here's our dresser. I'm going to represent it by a dot. I know that there is a force gravity pointed down on that dresser because it's on Earth. I know that the dresser is on a flat surface, so I should have a normal force pointed up from that flat surface. I also know that I am pushing this dresser to the right, so I'm going to have applied force to the right. And then I know that I'm going to have friction pointed back to the left. I know that friction is smaller than force applied because it's accelerating in the direction that I'm applying a force. The next step we're going to want to do is write our net force equation. So let's start with the x direction. Net force in the x direction, and I'm going to write subscript x so I know that it's in that direction, is going to be equal to the forces pointed to the right, in this case force applied, minus the forces pointed to the left, in this case force friction. And then we're going to go ahead and set that equal to mass times acceleration. And again, I'm going to put a subscript on acceleration here because it's only the acceleration in the x direction. We know that the acceleration in the x direction is not equal to 0 because it tells us that we're accelerating in our problem. Next, we're going to go ahead and write our net force equation for the y direction. So net force in the y direction is equal to the forces pointed up, in this case force normal, minus the forces pointed down, in this case force gravity. And we know that this is also equal to mass times acceleration. This time though, acceleration is in the y direction. So just to clarify, AY is talking about acceleration in the y direction. We know that AY is equal to 0 meters per second squared because in the y direction, we're at rest. Which means that our forces are balanced, meaning that force normal is equal to force gravity in this case. So since AY is equal to 0, it means that force normal minus force gravity equals 0. Therefore, if we add gravity over to the other side, we find out that force normal is just equal to force gravity. All right, guys, let's go ahead and take a look at a cabin of a small elevator that is secured to a motor by a cable and is moving up while slowing down. All right, something important to note about this is the fact that we have an elevator and it's secured by a cable. So a cable is going to mean a rope or a string, something like that. So that's referring to force tension. Another important thing to note is the fact that it is moving upwards, but it's slowing down. Slowing down means that our forces on this elevator are unbalanced. So if I were to draw a picture of this elevator real quick, I have my cable right here, I have my elevator, and from here, I have my cable, I have my elevator, and my elevator is moving up, so I'm going to draw some lines showing that the elevator is moving in this direction. Next, I'm going to go ahead and make my free body diagram. So on my free body diagram here, I have the cable, which is supplying a force tension upward, and I have force gravity pointed down. The question is, though, which one of these forces is bigger? Is it force tension or force gravity? Well, if my elevator is moving upwards, but it's slowing down, that means that I need a bigger force pointed in the downward direction. Therefore, force gravity is going to be bigger than force tension here. The reason is because the elevator is moving up, but it's slowing down. Therefore, in order for an object to slow down, it has a bigger force in the opposite direction of its motion. If an object is speeding up, it will have a bigger force in the same direction of its motion. Looking at our free body diagram, we can see that we only have forces pointed in the y direction. So if we have our origin, right, we see that the upward direction is the positive y, and the downward being the negative y, and to the right, the positive x, and the left, the negative x. There are no forces acting in the x direction, therefore the net force in the x direction is just 0. We can see that in the y direction we do have forces, and those forces are force tension and force gravity. We said that our object is slowing down in the y direction, therefore we're going to have a net force. And the net force in the y direction is going to be the forces that point up, in this case force tension, minus the forces that point down, which would be force gravity. And those are equal to the mass times acceleration in the y direction. Since this object is slowing down while moving up, we can also say that force gravity is going to be greater than force tension. This just means that once we start solving for this equation and plugging in our numbers, we're going to find out that acceleration is going to be negative. And it's negative, like we said before, because it's slowing down. So let's take a look at another example here where we have a rightward moving car that is skidding to a stop across a flat road with locked wheels. So our car is moving along this roadway, it hits the brakes, and then it starts to come to a stop. So stopped. We want to analyze what we're being told, again, to see if there's any important information in this problem. It says the car is moving to the right. It also says that the car is skidding to a stop. So skidding to a stop is referring to the fact that the car is slowing down. So let's go ahead and label the origin, right? Just say that our origin is here. It points up and to the right, just showing that the rightward direction is the positive x and up is the positive y direction. Now we can make our free body diagram. Here's our car. We know that the car feels a downward pull of gravity from Earth. We also know that the car is on a surface, so it feels an upward push from that roadway. And then lastly, we know that the car is skidding to a stop. So the reason it is skidding to a stop is because friction is pulling it backwards. So friction is what's slowing our car down. So let's go ahead and write our net force equations just like we've done before. So for the y direction, we have net force in the y direction is equal to the forces that point up, force normal, minus the forces that point down, force gravity. And that equals mass times acceleration in the y direction. Since our car isn't moving up or down, we know that this answer is just going to be 0 newtons. Which also means, right, that the acceleration in the y direction is just 0. Again, this makes sense because our car is not accelerating up or down off of that road. Since our net force is equal to 0 in the y direction, we can say that 0 equals force normal minus force gravity. Therefore, if we were to add force gravity to the other side, we find out that force gravity is just equal to force normal in this case. So force normal is just equal to force gravity, and that's the case because we are on a flat surface. It's important to note, though, that this will not always be the case. Force normal will not always equal force gravity. It's only the case because we're on a flat surface and no other forces are acting up or down on this object. Now let's take a look at net force in the x direction. So net force in the x direction is going to be all the forces pointed to the right. In this case, there's no forces, so I'm just going to go ahead and write 0, minus the forces pointed to the left. In this case, that's just force friction. And we know that this is equal to mass times acceleration in the x direction. Therefore, if we get rid of the 0, we can say that our net force in the x direction is just equal to negative force friction, which equals mass times acceleration in the x direction. This makes sense because our car is slowing down, and slowing down will give us a negative acceleration. So quick little recap. Make sure that you're writing your equation for both the x and y directions. Also, make sure that you are adding the forces that point up and subtracting the forces that point down. And in the x direction, make sure that you are adding the forces that point to the right and subtracting the forces that point to the left. The last important piece of information is that if an object is slowing down, it means that it is experiencing a bigger force in the opposite direction of motion. And then on the flip side, when an object is speeding up, it is experiencing a bigger force in the same direction of motion. Basically, what we're saying here is that speeding up will result in a net force that is positive, and slowing down results in a net force that is negative.